And so we finally get to the wave equation. This is a very important equation in physics. It'll come up again when we get to electromagnetic waves. It's a starting point for thinking about the wave nature of subatomic particles. Big stuff. This is the second of two videos in a section in Young and Freedman's University Physics that is describing the mathematical description of a wave. In the previous video, we explained and developed this equation, which has to do with transverse motion. Again, transverse motion means up and down motion. Thus the y of x and t, like a wave on the sea going up and down. So this is an equation to describe the position of that wave at any point in time, at any the position of the wave y as a function of x, that is how far you are out from its origin, and t, how much time has elapsed since it started. So the equation is, this is in the previous section, the amplitude, that's the maximum displacement, times the cosine of kx minus omega t. K is a constant that for convenience physicists have developed. It's basically 2 pi divided by the wavelength. 2 pi over lambda is what k is. X is the amount, again, how far you are from the origin of the wave, and then omega is the angular frequency, 2 pi f. If f is cycles per second, then the omega is radians per second, and then t, the time since the wave origins of the wave. Okay, we did that particular equation in the previous video. So we can use calculus. If you don't know calculus, just memorize the equations. But we can use calculus to get from this description of the position, the transverse position, to the velocity with which the position is altering up and down. And then we can also use calculus to get to the acceleration of the up and down motion. Okay? If you don't want to think about the calculus, and even if you do, these are the equations that you want to know for describing the up and down kind of velocity, acceleration, position of a wave. I guess this also will work for longitudinal waves, which are waves that are horizontal, but that's not important right now. Okay, by the way, you'll notice that this a cosine kx minus omega t down here is exactly the same as this thing up here. So we can substitute y of x and t down here, and that's a simpler formula, right? The acceleration, the transverse acceleration, is the negative omega squared, that is the angular frequency squared, times the position function. This is similar to something that we saw in the simple harmonic motion chapter. The negative omega squared x, I believe, was the equation there that described the acceleration of a spring, say, going back and forth. Okay, so this is the stuff to know. If you don't know the next two slides, this is stuff to know. Okay. Now we can. How do we do this mathematically? You can tune out if you're not interested in how we get them using calculus. But basically, you'll know from calculus that to get from position to velocity to acceleration, we take the derivative. So acceleration is the second derivative of position, and velocity is the first derivative of position, and acceleration is the first derivative of velocity. So there's a calculus, differentiation kind of relationship. First derivative, second derivative. Now, if you know the calculus, you also know that since x and t can both vary, doing the derivative of this can be really sloppy. Well, it can be complicated if you're treating both the x and the t as things that can vary. But calculus has this thing called a partial derivative. In a partial derivative, you treat part of this as a constant. So you say, okay, I'm going to hold the x constant, and I'm just going to vary the t. And you can do it the other way too. I'm just going to hold the t constant, and I'm going to vary the x. That's called a partial derivative. They're sweet. As far as derivatives go, they're sweet derivatives. I love partial derivatives, much better than the real deal. So basically, the way that we get from one of these to the next is by taking the partial derivative with regard to time. So the partial derivative of this with regard to time is going to treat the kx part, keep it constant, as if it doesn't change. And so the derivative of a cosine of something is the derivative of the stuff inside the cosine multiplied by the negative sign. So the derivative of the cosine is the negative sign. And so this, by the way, is how to write a partial derivative. It's a funky D. You basically take the D and you bend it a little bit. So this is how you write a partial derivative. It's a partial derivative with regard to time, which means that I'm going to treat the x as if it's a constant. And so the derivative of cosine is the negative sign, okay, there's where the sign came from, times the derivative of the stuff in here. So I'm treating that as a constant. That means the derivative of a constant is 0. So that disappears. And then you'll know from basic differential calculus the derivative of something like this with regard to time becomes negative omega. So the omega, that's where the omega comes from. And then remember I had the derivative of cosine is a negative sign, so I had a negative coming from that, and then I had a negative coming from this. Negative times negative is positive, and so it ends up being just omega times the amplitude times the sine of that. And that's how I got that formula on the previous page. Okay, now we can get the acceleration by taking the partial derivative of this with regard to time. So the derivative of the sine is the cosine. So that's where this cosine comes from. Sine is the cosine. This is the second derivative with regard to time squared, is the way you say that. This time squared really doesn't, it's not really squared. It's just, I don't know who came up with it, maybe Leibniz. Anyway, it's not helpful, but that's what they say. So the derivative of the sine is the cosine, and then the derivative of this again, this is going to go out because it's constant. Negative omega on the front, so there's the negative omega times omega makes omega squared, and we're back to what we had up here. Okay, so there's the math. Partial derivatives. If you know how to do partial derivatives, it's very straightforward, very easy. Okay, now you can also, these are all with derivatives, partial derivatives with regard to time, treating this as a constant. We can also do partial derivatives with regard to x and treat the time as a constant. And so if we do that, we're going to get equations for the shape of the wave. So this again is our starting formula for the position as it varies. If I take a partial derivative with regard to x, then I'm going to get an equation for the slope of the wave at every point. A partial derivative with regard to x. And so the derivative of the cosine is the negative sign. The derivative of this with regard to x, this is going to be a constant, disappears. Derivative of this is straightforward, it's k, multiplied on the front, so I have the negative coming from the cosine, derivative of the cosine, k coming from here, a coming from there, derivative of the cosine is the negative sign, sine comes from there, and blah, blah, blah. So there you have it. So this equation's not as important as the previous, equation, but it basically is an equation that's going to tell me the slope of this wave at every point. And then if I want to know that, so that's the slope of the wave at every point. If I take the derivative of that, what I get is the curvature of the wave at any point. Okay, so the second derivative, again, the derivative of the sine is the cosine. The negative carries over. Derivative of this, the k comes out. K times k is k squared, and so that's an equation for the curvature of a wave. Okay, well, this page isn't as important as the previous page. Okay, so that gives you the curvature of the wave. Now, the wave equation. Now we're ready for the wave equation. So if I divide the second partial derivative with regard to time, let me remind you what that was. Blip, dip, dip, dip. Okay, this bottom part is the second derivative with regard to time. If I divide that by the second partial derivative with regard to x, which is this bottom one here, if I divide those two, and if I remember that omega divided by k is the velocity, I'm not going to show it, it's in the book. If I take all that, whip it around, mix it in a bowl, I end up with this, which is the wave equation. It says that the second derivative of a transverse wave with regard to x is going to equal to 1 over the velocity squared times the second derivative of that wave with regard to time. And this is the wave equation. It works for not only transverse waves, well, let me tell you, it works for longitudinal waves as well. It works for electromagnetic waves. It doesn't have to be, it works for other waves other than sinusoidal waves, It doesn't have to even be periodic. This is a incredible equation. Whenever this equation works, we know that we have a disturbance that can propagate as a wave. So there it is. Remember it. Put it on your wall right here. The wave equation.